So we'll go ahead and begin this lesson with a discussion on constructors and destructors. These will be responsible for building up objects of our user-defined type as well as breaking them down at the end or their destruction. So let's go ahead and just talk about object initialization to begin with. Recall that when we define local variables of the primitive built-in types, they're not automatically initialized for this. Instead, they take on whatever value is left over in the memory in which they're going to occupy. The data members of an instantiated color object, RGB, are of type int. Accordingly, they are not going to be initialized when we instantiate a new object of the color type. When I wrote the RGB values of a color object in my program to standard output before setting them using our mutators, I observe the following. These are nonsensical values, and obviously they do not fall within what it means for this object to be of a valid color. So what we'd really like to happen is that on default construction, so if we were to write something like color C, we would like our G and B to take on some sort of sensible default value. This could be 0, it could be 255, it could be Aggie Maroon. It's something, but the idea would be is that from the point of construction, those values would be within the range of 0 through 255 inclusive. And then all members of the public interface would also respect that invariance such that we would always have a valid color object. So the uninitialized nature of variables and objects instantiated from our user-defined types is obviously problematic. When we instantiate an object from a user-defined type, it should be always initialized to some sort of valid state. For an object initialized from color, obviously we want those data members to be initialized with a valid value between 0 and 255 inclusive. We would then write the member functions of the public interface to ensure that the object's valid state is maintained throughout its lifetime. In other words, that the data members RG and B could never take on invalid values. And for the context of our discussion here, for color, that would be outside of 0 through 255. We're going to just strive to design our types so that values are guaranteed to be valid. And that's what I mean when I keep referring to this idea of an invariant. An invariant is simply a rule for what constitutes a valid value. So constructors, this is going to be kind of how we're going to build these objects up. It will essentially provide them with initialization or their starting state. So in order to initialize our data members upon object instantiation, so that is within a declaration. So at this point, we'd want C1 to take on valid values and for this object to be built up, because right after this line here, C1 is a full-fledged color object. It can do anything that a color object can do. So we're going to write a special member function known as a constructor. The constructor is going to be implicitly invoked whenever an object of that user-defined type is created. So again, its job is going to be to construct an object and to do initialization if necessary. Now, when we declare a constructor in our class declaration, we're essentially declaring a function that is going to have the same name as the class. It will not have a return type, which makes it one of these special functions, and it can have a parameter list with 0 or more items. So up until this point, we did not write a constructor for any of our classes. So what this meant was the compiler essentially was providing our class with a default constructor. The compiler generated a default constructor, calls the default constructor on all of the user-defined type data members. For the case of the primitive type, we do not have this, meaning that those values will be left undefined. The constructor that has been used when we instantiate a color object with the declaration color C, that would have been this compiler generated default constructor for us. It is important that we write our own default constructors though when needed, because we are going to know better than the compiler how objects of our type should be constructed and how its data members should actually be initialized. So when we talk about a default constructor, we're essentially talking about this special member function that is going to have an empty parameter list. So following from the slides on the previous page, recall that this special member function has the same name as the class. We can see here the declaration for default constructor. It does not have a return type. That's one of the things that makes it special. In addition to not having a return type, it's also special because it's implicitly invoked upon the construction of a color object. Notice here, it is a default constructor because its parameter list is empty. Now, when we go ahead and provide the definition for this, we're going to introduce what's known as an initializer list. We'll talk about the importance of this, but this is more or less, I believe, came into existence during C++ 11, and it's going to provide a way to directly initialize the data members. So once we hit the body of the constructor, these data members would go ahead and actually take on those values. It would be the same as writing int r is equal to 0. It's actual initialization. And we'll go ahead and distinguish this from not using an initializer list here shortly. But as always, kind of in our declarations, moving into our definitions in the corresponding source file, we see here that the constructor we are defining is scoped within our color type, as noted by the name of the type, followed by the scope resolution operator. The function for color that we're defining is color's default constructor. And notice here is a colon. Directly what's going to precede the colon is going to be the initializer list. This is simply going to be a list of data members. Directly preceding the name of the data member, the identifier, is going to be a set of parentheses. Within the parentheses is going to be the default value that we would like, in this case, the primitive typed data members R, G, and B to start out with. So again, this is going to be initialization. So notice here within this list, we say that R will take on the value of 0 upon default construction. G will take on the value of 0 upon default construction, and B is going to also take on the value of 0. I could have, it doesn't have to be 0. It depends on kind of the context of the type that you're creating. In this case, I decided it to begin as black, so all zeros. Alternatively, you could have started this as Aggie maroon, maybe UIUC red or blue. It would be kind of completely up to you, but whatever you're doing here should be sensible. The values that the object are starting with should go ahead and respect any sort of invariance that you're expecting that these objects derived from this class should respect throughout their lifetime. So in addition to kind of default construction, we also have the ability to overload the constructor and actually pass in arguments to it when we're initializing or constructing objects from a user-defined type. For instance, I might like to go ahead and say color C1 is going to start out with 248, or heck, let's go 8000 for Aggie maroon. And somehow we'd like to go ahead and get those arguments into the correct data members to start out this color object with 80, 0, and 0 for R, G, and B respectively. So a constructor is a member function. As we've talked about before, curly braces in C++ denote a scope. Functions that have the same name but different parameter list and appear in the same scope are overloaded. Therefore, it follows that we can overload the constructor of a user-defined type, and a class can actually have more than one constructor. So we can have default constructions, so we could do something like color C2, or parameterized construction, where we could go ahead and pass arguments to a parameterized constructor. So the declaration for a parameterized constructor is probably follows from what you're probably think at this point. We see here that we're going to provide a overload. We're going to go ahead and overload the constructor. So we're going to have the same name, color, followed by a different configuration of the parameter list from the default constructor. In this case, we're going to have a parameter that will have 3 integer arguments passed to it when it is invoked. So the definition for this parameterized constructor will fall within the corresponding source file, as one might expect at this point. You can see here, we go ahead and prefix the name with the type, who this constructor is being defined for. In this case, it's colors constructor, parameterized constructor as kind of denoted by its name, but we still need to inform the compiler of that because it would have been perfectly valid to have a function named color within this file that takes in 3 integer arguments. That would be completely possible, though probably not sensible nor reasonable for this application. But to distinguish if that were to happen, we go ahead and scope this to color. So here's our parameter list. And again, I'm going to go ahead and draw attention to the initializer list. So directly following that last parenthesis there, we have the colon. And then we go ahead and simply list out the data members. And you don't have to list them all, although you probably should. And if you're not listing them all in this constructor, you probably should be providing some sort of default value for them to start out with. I mean, that's complete, that would make sense here. But in this case, we're simply going to say that R is going to start out with the value stored in the parameter R. G, likewise, we'll go ahead and start out with the value stored in parameter G. And B is going to go ahead and get whatever is in parameter B. Notice at this point, the values for R, G, and B have been set respectively with their values stored within those parameters. We have to go ahead and ensure that because the user is passing these in, remember this is a parameterized constructor, so the user is specifying the initial state of this object. It would be a sensible thing to ensure that, hey, if the invariant is these objects will always have valid values for R, G, and B, well, we need to obviously go ahead and ensure that the values for R, G, and B are in fact valid. We can do that with a simple conditional, and we can throw an exception if if this violates our invariant. Notice that, understand that if an exception is thrown during construction of an object, so during within the constructor, that object will not be created. So I want to draw attention to this, and this is definitely what I expect you to avoid in this course is pre-C++ 11 initialization, shall we call it, because what's actually really happening here is assignment. So if we go ahead and look at the pre-C++ way of going about this, you can see a default constructor, you can see a parameterized constructor. In both cases, there's no initialization list. So what that means is right here and right here, the values of R, G, and B, the data members, is undefined. We don't know what they start out with. They start out with essentially whatever's left over in the memory region allocated for them. So they're initialized with undefined values, and then in either the constructor or the default constructor or the parameterized constructor, we then assign. This is assignment. This is not initialization. We assign values to R, G, and B respectively. In the default, some sensible starting value, and the parameterized whatever's within R, G, and B. The parameters R, G, and B. Notice here that I'm not showing, the checks on whether or not those values were indeed valid, but yeah, you should ensure the invariants are maintained. So do not use the pre-C++ 11 means of going about writing these constructors. Ensure you are using the initializer list so that actual initialization is occurring and not this two-step process where essentially we're initialized with undefined values first, and then we make some sort of assignment to them. So this is the preferred way. I'll go ahead and say, don't do that. Maybe not right over 11. Maybe make that red. do not do that. We want to go ahead and follow the C++11 and later means of doing that. And again, that is using the initializer list here. That semicolon following by the list of data members and the values that we'd like to start out them with. So at this point, you might be going, hey, I saw you do this before. What is the difference in using curly braces instead? Curling braces, universal initialization here, is going to prevent narrowing conversions to occur. So in this case, no narrowing conversion is going to occur in the default constructor because, well, 0 is not, say, a floating point value. However, if using again, performing in the initializer list with these curly braces, if you were to write color C1, go ahead and say 2.4, 8, 10, this would go ahead and give you a compilation error because 2.4 would be narrowed if we're trying to initialize R with that. So braces are always kind of helpful if we're looking to avoid narrowing conversions because they will not allow them to occur. So one other thing to be aware of is classes without a default constructor. The second that we define any sort of parameterized constructor, the default constructor that the compiler once gave us is no longer given to us. So if we define any constructor for a class, the compiler will not generate a default constructor for us, meaning we'd have to go about and write one. If we define a parameterized constructor for color, but not a default constructor, we will not be able to initialize an object or instantiate an object without providing the necessary arguments. Without a default constructor, so let's just for the moment consider our parameterized constructor for color with 3 integer parameters. We could not then write something like, hey, I want a vector of colors, and I want it to start out with 100 colors. Why? Because if we're initializing this vector of colors, 100 with 100 of them, we need some sort of way to essentially create 100 colors. And because we do not have a default constructor, we would essentially have to list out 100 colors with values being passed to its parameterized constructor. So color in this case is not default constructible. So if we wanted to create a vector of colors in this sense, and we did not have a default constructor, we'd have to go ahead and list out the colors explicitly that we'd like to place within it. So the one other kind of special function we'll talk about today is going to be destructors. I'm going to go ahead and point out that we definitely did not need a destructor for our color type. We will need it later on in the semester when we begin talking about dynamic memory within classes, or really acquiring any sort of resource. C++ follows the RAII kind of paradigm, or it's what's recommended. Resource acquisition is initialization. So if you're going to say your type is going to grab some sort of resource during instantiation, let's say it's a file, dynamic memory, or otherwise, we typically go ahead and grab that resource in the constructor, and then we go ahead and typically release the resource in the destructor. We're not doing any of this within color, but I think it's important to at least introduce a destructor at this point. So the destructor is another special member function, and it is obviously called when an object's lifetime is up. So constructors implicitly called upon the construction of an object as it's being built up, and then the destructor would be called essentially on the demolition of that object or when it's torn down. So we kind of talked about the primary uses. There's going to be only one destructor per class. It cannot be overloaded. So that's kind of another caveat to it and what makes it also special. So just like the constructors, the destructor is not going to have a return type. It's special in this sense too. To declare a destructor, we go ahead and write tilde followed by the name of the class. So color. and in this case, empty parameter list, in every case for the destructor, empty parameter list. When we go ahead and define this function in the corresponding CPP or .cc file, we go ahead and scope it to our color class, write out the name, and then define what it means to destruct this object. So again, I'm not going to write anything kind of within this. If you're tinkering around at home, put in the cout statement and just confirm that this special function is indeed called when an object's lifetime is up. Again, where we'll see this be useful is essentially when we're getting into dynamic memory and we're seeing in resource allocation or acquisition rather within the constructor. We'd go ahead and see the release of that resource in the destructor. But don't worry about that just yet. Just understand, focus on constructors. They're going to be the big point, kind of big thing until we get to that point, because they're not only grabbing resources, they're actually setting up the initial state of the object or the initialization of that object. And to respect any sort of invariance that we might have on that type, we really need to begin enforcing them at the time of construction.